Alrighty, let's make a start. So today is a review class that would be for covering the continuous probability stuff and also the unit 1 and 2. What do we do then? I think it was the logarithms exponentials review. I don't think we've actually moved on to unit 1 and 2 derivatives as of yet. But there was some other topics within probability, specifically continuous probability, that we didn't touch on last time. Last time we focused on pretty much entirely just on the calculations of probabilities of the of continuous probability, just how we calculate those kinds of probabilities. The other side of that is the statistics. So just like how discrete had the mean, variance, standard deviation, that sort of thing, we also have the same statistics for continuous, and those are calculated in a very similar way, but there'll be some similarities, but we'll often be using integrals because, once again, continuous probability uses a lot of integration. Starting with the mean, or the expected value. Pretty simple, actually. It's just the full integral over the full domain of x times f of x. That's pretty much it. So if your function is this truncus over here, and you want to find the expected value, or the mean, all you're doing is taking that function into an integral and then multiplying it by x. That's the whole thing. Depending on how complicated that function is, it might be doable tech-free. In this case it is. If it's not so doable, then it's very likely to be a tech active, in which case you just cas solve it. Well, not necessarily cas solve, but evaluate it using just the cas integral. The boundaries in this case are 1 to 2, because that's what the effective domain of our probability density function is. And that's pretty much it, yeah. So just like normal, you would find your capital F of x, antidiff, and then the top take bottom. We're doing a lot of definite integrals in this area of study. That gets us our expected value. Any questions so far? Alrighty. This is sort of me just covering it just because it's technically possible to show up in the chapter section. This is not something you'll really get when it comes to doing your actual exams, with one minor exception, and that being the application of it with the variance. How there's going to be a certain way of doing it. But we'll worry about that in a moment. For now, just in case you do get this assigned to your as your homework, the way you do the expected value, rather than just e of x, but let's say you have some transformation on that, ax plus b for instance, or just some regular old g of x, instead of doing x times f of x, you're now doing just whatever that function is, times f of x. That's the generic way of going about it. For linear, there's also a further simplification where instead of doing function times function in the integral, if that function is a linear, then you can solve your e of x, your mean, as normal, and then just multiply by whatever the a coefficient is and add whatever the b coefficient is. Here's an example of that. If it asks you to find e of 2x plus 3, the simple way of doing it, perhaps, depending on if you're doing tech-free or tech-active, could be just to slap the 2x plus 3 out the front of f of x as your multiplication. In this case, this is something you could do relatively easily tech-free, so I've got the fully worked solution of that. You would just expand that through to your function, split the fraction, and then, well, 1 over x just goes to log 1 over x squared. You would probably want to rewrite that as x to the power of -2 to get a better idea of what the rule would be for anti-diffing that. Then, once you have your capital F of x, just like before, you're just subbing in the integral bounds. Alternatively, if you want to use the linear simplification, you just find your e of x as normal by doing x times f of x. evaluate that over and over again until you get to the final stage where you're now distributing that multiplication of 2 through and adding 3 at the very end. And what you'll find is you get the same answer with marginally fewer steps. Again, this is something pretty much exclusive for the textbook. You don't really see this being needed for the exam. Next up, median and or percentiles. So this is something that's pretty much exclusive to continuous probability. We don't look at this for discrete. The median is you actually solving the middle value of your data set, and it's got to account for a total of half of total probability in your given scenario. So if you want to find the median, what you're essentially doing is solving for the upper bound such that your total area under curve is equal to a half. You want to find whatever upper bound gives you that. The median is a specific percentile. It's the 50th percentile. So if a typical question is asking you for like the 70th percentile or whatever, basically whatever the number is they give you is the decimal that you use to equate your integral to. It might not even be the case that they use the keyword percentile. We've seen a question like this before, which was worded purely using the math notation. Here's a version which is worded just purely worded, right? So you have your duration of sales calls given by this particular function. Find the value of A such that 90% of phone calls last less than A minutes. This would be effectively the 90th percentile. Find the value of A such that 90% of phone calls last less than A minutes. Less than means A is the upper bound, and so you want to go from your upper bound all the way to the absolute lower bound, in this case 0. And because you want to find it such that 90% of phone calls last less than, you're now using 0.9 as the thing that you are equating to. In a tech-free, this would be a matter of, again, anti-diffing the integral, and then just doing your capital F of A minus capital F of 0. But because we know it already equals 0.9, we can actually put that in an equation and equate it to 0.9. Sub in, simplify, 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 you'll get some logarithm answer. If you're doing a tech-free, anyway. Tech-active, obviously you're just going through and evaluating that on the CAS and giving it in either decimal or exact, depending on what's being asked. Tech-free is usually a bit weird. Negative natural log 0.1. It's not immediately obvious that that's going to turn out to be a positive value, unless you spend a lot of time working with logarithms. Any questions on these percentiles slash median kinds of questions? Easy. Next up, variance. You would have seen a similar equation to this when we looked at it at discrete. This is the integral version when we use it for continuous. Now, last time when it came to discrete, I advised not using this version of it, rather doing e of x squared take e of x all squared, the expanded version, and you can absolutely do that here as well. It's just that every variance question that's ever really been asked has been tech active, and just doing this tends to be a bit easier because what you're doing is evaluating a single integral rather than evaluating multiple. So that's why I've just got this version up here. It's easier, and I'm pretty sure this is the one that shows up on your formula sheet. Let me validate that real quick. Exam formula sheet. Continuous. Yeah, it's the one that actually shows up on your formula sheet. Same thing with discrete. Discrete doesn't actually have the... oh, there it is. Yeah, here's the generic variance. So you can either do this version where you do e of x take mean all squared, or you can do e of x squared take mean squared. That's true of all of these variances here. Obviously you definitely don't want to do that for binomial. Binomials are much easier to do that way. But both of these have their options. It's just the case that because this is usually such a complicated coefficient, can't really highlight that, because this is usually such a complicated coefficient, it's a TeX active thing anyway. And so you might as well just go ahead and use this version. Anyway, so that term there is the mean, it's the expected value. So what you're going to want to do is evaluate the expected value first before you then go ahead and try to evaluate the full thing. So you do expected value, x times f of x if you haven't already got a copy of it. In this case, since it's the same function, we technically already had that, so we'll just copy that down, put it in the spot where the mean, where the expected value goes, and then once again evaluate via the CAS. Variance of a function, again this is just exclusively textbook. Instead of doing what is it? So instead of doing x take the mean, x take e of x, you're now doing g of x take e of g of x squared, or the only actual question the textbook will give you will be the one that has a linear transformation on that, in which case you just use this simplified version here. You ignore the b entirely and just put a squared on the way that you would normally do the variance. I've done both ways of doing it here. It's not particularly great, so better off doing the linear simplification version, where you calculate the variance just like normal, pretending none of this exists at all, and then only at the end do you just take this coefficient here and you multiply by the square of it at the very end. Again, textbook exclusive, so no need to put too much thought into that. Second to last is going to be the standard deviation. Standard deviation is always the square root of variance. So we've already had a look at variance, it's just that equation. So if you want to find the standard deviation, you are just square rooting that equation. That's pretty much it. I'd recommend not necessarily putting in this all in one line. Usually it's better to find the variance first and then square root it at the end. If you try to put too much onto the CAS at the same time, it's likely you'll make a syntax error, and then that's less than ideal. Yep, this is the last one up. This is the interquartile range. This is technically nothing new. This is just you finding two specific percentiles and then performing a subtraction. That's it. It's the distance between the 25th and the 75th percentile. So you equate your integral to 0.25, solve the upper bound. You equate your integral to 0.75, solve the upper bound. Take those two values, perform a subtraction between them, and whatever comes out is your interquartile range. Fairly straightforward. And this will likely be a CAS thing as well, simply because of how much integrating would have to happen, and 0.25 and 0.75 aren't necessarily nice and easy values to work with tech-free, depending on the function you're provided. Anyway, that's all the statistics there. I've got a nice little cheat sheet at the end for all the stuff. Is there anything in there that needs further clarification before we get into some questions? I'll actually do a screen grab of the summary sheet because we covered a fair few different equations. Cool, okay. Got that in the chat for you guys to refer to. let's have a look and see if we can implement it. Yeah, like look at some of this stuff. They give you some proofs, which is kind of nice, but obviously you don't necessarily need the proof, but it's kind of nice to see that it exists. Jeez, look at that. Crazy. Yeah, here we go. This one actually, they did do, and when it comes to finding the variance, they did actually do the e of x squared take mean squared instead. So I guess you can also see an example of what that would look like. Find variance and standard deviation of this function. So if we're doing variance using this approach instead, to find e of x squared, basically put, instead of doing x f of x, it's now x squared f of x. We saw this before. Whenever you put some sort of transformation on your e of something, your e of x, you basically just replace whatever the multiplication is. X squared times 0.5x, that's going to get you out to 0.5x cubed, of which they've just taken the 0.5 out the front. Integrating over 0 to 2, because that's what the domain is. Anti-diff your x cubed to 1 over 4 x power 4, and then yeah, just do your capital F of 2 take capital F0. That gets you the first component of variance. Apparently they're also going to borrow an example, an answer from a previous example, just doing the regular e of x. So regular e of x would just be saying, instead of squaring this, you just do x f of x. And if you do that, apparently you're going to get 4 out of 3. All you're going to do from there is square that. I don't know why they're using the keyword e of x here, but using the mean value, the mean symbol here. These are the same thing, e of x and mean. So when you see mean squared, it's just taking this value and squaring it. We now have both of these. We perform a subtraction between the two. That gets us our variance. As for standard deviation, it is now just the square root of the variance. So square rooting 2 over 9, getting us root 2 over 3. Cool. Let's give this a crack. Random variable x has the probability density function, basically just 2x from 0 to 1. Find variance, hence find standard deviation. Oh, question. Can you go over variance equations again? Today's sack was a tough one. Sure, that's fair. So there's two different ways of doing variance. One is generically across the board. You can do e of x squared take e of x all squared, or mean squared. That's the way that was presented here. And it's fine to do it that way. It splits things up even further. Alternatively, you can just go for broke right off rip and just use this equation here, where you do x take the mean, so you still need to find the mean. X take the mean all squared times f of x, and then evaluate that integral instead. So we'll just do that here as well. So we've seen the working out for that one, where you split it up into a bunch of different things. Alternatively, if we do it using this equation here, what we need from that is the mean. So if we go back and have a look at what the mean actually is, the mean is e of x, it's just x times f of x, whatever our function is. So let's go ahead and do that for this function. X times f of x is now just x times 0.5x. So if I go ahead and do that, it's the integral from 0 to 2, since that's our domain. Don't understand the purpose of the factors. Yeah, that's totally fair. Yeah, that's pretty fair. So variance, standard deviation, these are measures of spread. They're trying to essentially say how far from the mean is your probability distributed. So like if the mean has like an 80% likelihood of occurring, then that's pretty low variance because pretty much all the probability is condensed right on the mean. Whereas if the mean had like a 20% chance of occurring, then that probability is now distributed elsewhere in the distribution and thus has higher variance. And so to explain a little bit about what the equation has going on for it, x take mean squared means that you are finding the distance between your outcome and the mean squared. You're finding the squared distance between the outcome that you have and the mean. Multiplying that through by f of x is basically the same as then multiplying through by the probability, so to speak. Kind of like how when you do the discrete mean, you do like your x times f of x times the probability. That's kind of like what's going on here. And because it's integral, you're essentially summing that up across all possible outcomes. That's probably the best I can do to explain like what is, like why this is arranged in the way that it is. It'd be more so better off you guys, if you're interested in like the reason for these equations, you'd be probably better off looking up videos of people diving into the actual theory behind this sort of stuff. It's a little bit hard to explain it at a I mean, partially because I just also haven't looked into it too much myself. What's real-world application of probability density functions, variance, standard deviation? What might some of the extended response questions applying these concepts look like? Yeah, okay, so real-world application of this sort of stuff. So the example that I pretty much always give has been your grade distributions. So just naturally, when it comes to grade distributions in a given cohort, they are extremely likely to essentially conform to what is referred to as the normal distribution. It's a special function that matches this sort of shape here, the bell curve, so to speak. And so anytime there's a SAC, let's say, there's an average grade for that SAC, right? That's going to be the mean. Let's say your average grade was, I don't know, 60% in the cohort. That would put 0.6 as the dead center of this distribution. From there, there's going to be a certain spread from the mean. Some students are going to do better than others, some students are going to do worse than others. Calculating the standard deviation, the measure of spread here, can essentially tell you, proportionally speaking, how much better you are doing compared to everyone else, or how much worse you're doing compared to everyone else by a certain number of standard deviations. And the fun thing about specifically the normal distribution when it comes to standard deviations is that the spread that is represented by those standard deviations actually has fairly consistent groupings, in the sense that having a grade value that is plus minus one standard deviation from the mean, 68% of all grades in your cohort are going to be within plus or minus one standard deviation. 95 are going to be within plus minus 2. 99 are going to be within plus minus 3. And, you know, depending on what slice you are in this, shows you the likelihood of you being in that particular, in that particular slice. That's why your study scores, like getting to a 30 is typically around the mean, whereas getting to a 40 puts you top 9%, getting to a 45 might be, it basically just gets exponentially harder and harder to achieve the next grade. That's effectively what we're seeing here, where each individual standard deviation that you climb up or down is disproportionately harder and harder to obtain. You're essentially graded to this kind of curve. And it's not even that like we're forcing this to happen. This is just what happens naturally. Grades just tend to be distributed like that. So that's a bit of the real world application there. Rule 40 is the goal. Yeah, no, that's fair. Get Rule 40 for sure. And yeah, as long as you're consistently working towards it, doing all the extra practice, it's achievable, you know. Definitely keep at it. As for like what the kind of question flow is, what you'll typically see is it will be, I have this even written out in my probability guide, where what you'll see is typical groupings of the probability types. So what you'll see is discrete, binomial, and this other topic, sampling and estimation. They will be grouped together in the sequence of questions. And then once they're done answering or asking questions about those particular things, they'll introduce a new topic header, which will start looking at the continuous aspect, right? They'll start doing continuous and normal distribution and playing back and forth between those. And so if I pull up, let's say, just any old TechActive exam, we can walk through what that looks like. Yeah, okay, cool. So you can see off rip, continuous random variable, it's starting out with continuous. Find the mean time taken. All right, we've already just talked about finding the mean. It's just x f of x, or in this case, t f of t. Find standard deviation. Well, that's just going to be the variance, like we discussed earlier, and then square rooting it. Variance meaning x take mean, so we already have the mean. So it would be a matter of doing x take that value that we just found, squaring it, and then multiplying by the whole function, which would be this thing. That gets you the variance, then you standard deviate by square rooting. From there, what else is it asking? Driver allows k minutes to travel to work each day. If the journey takes longer, driver will be late. Whether the driver is late is independent. If k is 47, write a definite integral to show the probability of the driver being late. So this is the time taken to travel to work. So these t values here are all about how long it took to get to work. So if k equals 47 means that you are late, then journey taking longer than 47 means you're now doing 47 to 59. Right, taking anywhere from 47 to 59 would be considered late, and what you're hoping for is that integral ends up equaling. If you integrate from 47 to 59, that should end up equaling this value. Next up, if k is 47 still, find the probability the driver will be late on at least one day in a 5-day working week. This is where things get a bit nasty. This is where what they've now done is convert your continuous probability and taking a step up into now discrete, because it says late on at least one day in a 5-day working week. We've just calculated or been given the probability of late. Now we're evaluating that over multiple days. Because we're evaluating that over multiple days, this has now become discrete. Day 1, day 2, day 3, day 4, day 5. So you use this value as your p-value, probability of success, or in this case probability of late, and you now use binomial methods to solve this. So this is what they end up doing. You got to keep your head on a swivel for when probability types end up changing. It's been continuous here, continuous here, continuous here. Now that they've worded it in this way, you are now using the results from previous answers in the continuous probability space, but because they've now broadened the scope in a certain way, it's now turned binomial. This stuff we haven't talked about at all. P-hat is hallmark of sampling and estimation, but yeah, we'll say yeah, we'll just sort of leave that there until we actually explore sampling and estimation specifically. But you can see how the probability types are going to change from question to question, and you've got to look for particular wordings to see that. What else? Find integer k such that probability of the driver being late at least once in any 5-day working week is 0.2. So this is stacking up yet again another layer of binomial, because at least once in any 5-day working week, now you're looking at 5-day working weeks as a whole rather than a single 5-day working week. And then it just keeps going. Part C, Part D. What else have we got? It'll say the keyword normal distribution. Now all of a sudden you pretty much ignore everything unless necessary. We're now looking at traffic time, traffic light wait times. It's normally distributed, so we now use the stuff from normal distribution, which we still haven't talked about yet, so I won't get into too much details as to how you solve this one, but it says the keyword normal distribution. You're now doing normal distribution probabilities. And then even just looking at this table, you can see it's discrete. So now calculating things in a discrete method. They'll just continue to cycle through the different probability types, and it's your job to look for those key things that indicate certain probability types are being mentioned. That's in the tech active section. Tech free, I think, does a similar thing, but just not as many questions. Let me have a think. Okay, so we got some discrete. Yeah, okay, they just separated across different questions. That one was fully discrete. This one, binomial, it literally tells you. And continuous. They actually tend to like to throw some transformations questions into continuous. They've done that a couple of times. They're less than pleasant to deal with. Anyway, that's where that's headed. Don't feel too confronted by it. The more you practice these, the easier it'll be to see what you actually do to what you need to look for to identify what's being changed. But okay, we're not quite there yet. So let's just do some of the individual chapter sections and work our way there. Okay, so random variable has the probability density function given by basically just f of x equals 2x from 0 to 1. Find variance, hence find standard deviation. So for variance, it is it really depends on which equation set you want to use, whether you want to use this version here or this version here. Either way, you still need to start by finding the mean, which is x times f of x. So let's do that. So we're doing from 0 to 1, x times f of x, where f of x is just 2x. So x times 2x, and that got us our mean. To then plug that in the variance equation, if we scroll up, we are again integrating over the full domain. So 0 to 1. This time we are now doing x minus the mean. Whoops, I can't really grab a copy of it like that. Let me just manually type it out. X minus the mean, all squared, and then times f of x. I'm copying that from the top of the screen share. Times 2x dx, and that gets us our variance of 1 over 18. To then get the standard deviation, it's just a matter of square rooting that value. So you can see it's not really too bad to use this version of it. Whereas if you do e of x squared take mean squared, is it the same amount of work? Means then you're squaring it. It's a little bit more work, I would say, to do the expanded out version, specifically for continuous. For discrete, absolutely you want to do it this way, the split version. But for continuous, not so bad to just do it this way. Okay, next up, continuous random variable given by 3x squared, again from 0 to 1. Find a such that the probability of x less than or equal to a is equal to 0.25. This is a percentiles question. The 25th percentile is what you would be finding here. So if we have a look at what that entails, you basically just set the upper bound as the variable to be solved, and the equal sign is going to go to whatever the percentile is. For median, that will be the 50th percentile. For this, we're even being told, make it equal to 0.25. Since it's x less than or equal to a is an upper bound. So, cas solve, integral from, so lower bound is 0 in this case from the domain, upper bound is going to be a from the question itself, and it is the function, so 3x squared dx, and that is equal to 0.25 comma a, and that would be the upper bound, roughly 0.6. So good to get like a rough decimal there just to make sure that it does still fit within the actual domain you expect, 0 to 1, which 0.6 of course does. Find b such that x less than or equal to b is equal to 0.75. The phrasing is effectively identical. You're just replacing a with b and 25 with 75. That will give you 0.9, which makes a lot more sense to be a bigger value because you're accounting for more total area. Part C, find the interquartile range of x. Well, 75th and 25th percentiles, that's what the interquartile range is all about. You're finding what those percentiles are, and then you're doing a subtraction between them. That's it, the bigger one minus the smaller one. So if we get this and then subtract the other one, we will get our interquartile range. Yeah, of course. Okay. That's going to come out to be 0.278. Any questions? Question 3, we now have a split. We have 0.5 e to the x for x less than or equal to 0, and we have 0.5 e to the minus x for x greater than 0. Does say sketch the graph. Yeah, why not? That's fine. Actually, I wonder if I make this a piecewise, will it sketch nicely? 0.5 e to the x for x less than or equal to 0, and 0.5 e to the minus x for x greater than 0. H of x. Hey, look at that. Actually, alright. Let's make this a bit easier. There we go. Cool. Find interquartile range. So I'm hoping that making it a piecewise, the integrals will still come out proper. Let's see if that's the case. So again, we're looking for like the A and the B, right? The 25th and the 75th percentile. So it should just be a matter of saying function equals 0.25 and then solving for A. Is it gonna do it? If I control enter, yeah, it will. It just won't give me an exact. Maybe, is that fine? Yeah, that's fine for interquartile range, especially since it says give to 3 decimal places. As a quick sanity check, does A being 0.69 make sense? I don't think it does actually, because we should have symmetrical area on both sides, so the 25th percentile you'd expect would be a negative value. What happens if I do 75th? Yeah, okay. Lesson learned, more or less. Don't use piecewises when it comes to evaluating these integrals. Figured I'd give it a shot just to see if it worked out, but not so much. So better off instead using your understanding of where these boundaries are going to or should occur. And what I mean by that is, if I now try to copy this down into handwriting, because the CAS is now... Oh, they came out with something. Yeah, no, okay, nothing. So knowing the symmetry nature of this, essentially, rather than using a full piecewise, the 25th percentile is going to belong to the first function on the left hand side here, the one that goes x less than or equal to 0, because we can already see it's a 50-50 split of area. So to evaluate that properly, what you would be doing would be grabbing this, instead of using the full piecewise, just use the part that is on that left hand side, 0.5 e to the x. That's a much more sense-making answer, a being equal to 0.4. Oh, no, still bad. I figured out why. Putting 0 as the lower bound is not correct. X less than or equal to 0 means that you cap out on the bottom as negative infinity. That's what was going on. My apologies. We definitely wanted a negative number because we wanted to be left hand side of the x-axis. There we go, that's fixed that issue.
Chris, could you just stay on that screen just for 1 second?
Yeah, certainly.
Yep, we've got it down. Thanks.
Sweet. Now, the next bit, doing the 75th percentile, we would normally run into another issue, right, with the CAS, which is you're now encompassing the full left-hand side function and a bit of the right-hand side function. The good news is, because of the symmetrical nature of this, is that you already know 50% of the area is accounted for this left-hand side. And so if 50% is already here and you want a total of 75%, what you want now is from 0 to some value equaling 0.25 to make up the total. 50% over here, we don't want to use this function at all. We just want to use the right hand side function. And so making this equal to 0.25, which is kind of like what I actually did over here before when I did 0 to a 0.25. Now that sort of makes sense why that value ended up being what it was. I wonder if it'll still be the same, or if it just kind of broke last time. Anyway, it was still 0.5, but it was e to the minus x. It's going to be from 0 to, we'll use b this time just so we've got a difference. And yeah, we can actually see the symmetry of that as well. because it was exactly 50-50 split, the 25th and 75th percentiles are equidistant from each other from 0. So if you can't use piecewizers, or maybe it was just because I broke the piecewise itself by trying to do what I did. I wonder if maybe if I had just made this negative infinity, would that have just worked? Well, I'll test my CAS and see if it works. Okay, that might spin for a while. Let's see if it spits out the right value. But yeah, if this does become a persistent issue where it does take quite a while, this is what you do. Never mind, it's actually fairly fast. So that was actually just my fault for not putting the right boundary on it. So yeah, so long as the function, the piecewise that you're working with is sufficiently easy, right? There's no like super massive function that you're smashing into each other, then even my old CAS seems to be able to evaluate it fairly well, so long as I actually give it the right thing to work with. And so yeah, so long as you can do that, feel free to just evaluate it directly. If the piecewise is sufficiently difficult, or maybe you're doing it tech-free, this is where you start splitting things up into the into the area components. Excuse me. Oh yeah, to actually do the interquartile range, it's just the first one subtracting the second one. Because they are equidistant, it's effectively just doubling the first. So we take our B value and subtract our A value. Not this one, this was me just not changing the thing appropriately. Subtracting our A value, we can see that one's just the negative of the other, so we're effectively just going to double it. Okay, next up, question 4. Okay, we got k over x, find the value of k. Ah, yes, it's been a while since we've done a question like this. So, when there's coefficients other than just x, well, I guess that's a misnomer. Any coefficient would not include x. When you're trying to solve for that coefficient, when it comes to continuous probability, it's pretty much always going to be the case that you just make the area under the integral equal to 1 over the full domain, and then solve for k. That's because the area under a full curve for a continuous distribution needs to equal 1, because it's representing all possible outcomes for the given scenario. So, CAS solve, shift plus for the integral, 1 to 9 is the domain. The function is k over x dx. It's going to equal 1, and we're solving for k. And that gives us our k value. Find mean and variance. We've done this before, but now we've just got a slightly weirder function. So I'm just going to define k as we found it, and move on to mean and variance. So this is less of a solve, more of an evaluate. So still from 1 to 9, the mean is always x times f of x, so x times k on x. We can see ahead of time that's already just going to cancel out to just integrating k, but whatever. And that gets us our mean, x times f of x. For variance, it's a bit more long-winded. 1 to 9 of bracket x minus the mean, which we just found. So Control C, Control V, x minus the mean all squared, and that is now times f of x, which is k over x. And that's obviously going to come out much more strangely. It does say 3 decimal places, so you would be control entering on both of these. Mean, variance. And then yeah, everything else is just more questions like that. Interquartile range, you're finding the 25th and 75th percentiles, mean, x times f of x, variance, x take mean all squared. I did square it, yeah? I did, yeah, cool. X take mean all squared, and then times the function. Okay, question 9 seems it's got a bit of interesting stuff to it. Find k in terms of a, so again, this is a thing where you're finding a coefficient, you want the area under the curve to be equal to 1. So let's see how that plays out. Menu 3, 1, solve integral from, this one's from negative a to a, negative a to, well, hang on, maybe before I do this I should undefine k, delete that variable, so we don't bugger that up. Shift plus negative a to a, the function is k times a squared, take x squared. Area under the curve needs to be equal to 1, comma a, oh not comma a, sorry, comma k, finding k in terms of a. And there we go, that's our k in terms of a. Now find the value of a which gives a standard deviation of 2. That's another story. So to make life a touch easier, I'm going to define the function. So it was k times bracket a squared minus x squared. That way I don't have to write it out a bunch. So, value of a which gives a standard deviation of 2 means we want to create a standard deviation equation. Standard deviation is the square root of variance, and variance, we've seen that equation before, we know that it means it needs the mean. So we've gone from standard deviation to variance to now needing the mean. This one had a fair few little step backs we needed to do. So let's get the mean. This one is from negative a to a, x times f of x. And that will get us our mean of 0. That's kind of fun. Cool. That makes the next one easier, because when we go ahead and do x minus the mean, if the mean is 0, then, well, the mean is 0. Still got to square the set of brackets. That gets us our variance. Square rooting it gets our standard deviation. And then finally, setting this equal to 2. Yeah, setting this equal to 2 and solving for a, since we wanted the standard deviation to be equal to 2. And that gets us plus or minus 2 root 5. Only one of those, yeah, only one of those values is going to make sense. Do we take the positive or the negative? Why? Think about what implied restrictions on a there are. If we think about the domain of a from negative a to positive a, because the domains go from left to right, it means that negative a needs to be a smaller number than positive a does. So if a is itself positive, then negative a becomes negative, positive a is positive. Whereas if you choose the negative root, negative 2 root 5, negative a now becomes a positive number, and positive a is now a negative number. Suddenly your domain is back to front. And so the only one that makes sense to take here is going to be the positive root rather than the negative root. Okay, almost there. By the way, 15Ds are nothing. It's it's so much for nothing. Only do this if your teacher's asking you to do it. This is where they start introducing all this sort of stuff going on, proofs for the simplification of variance and stuff like that. They are less than pleasant to do and never show up on an exam. Anyway, we're almost there, so I might as well finish off question 10 here. This one does appear to be a fairly simple piecewise, so maybe it is worth just doing the piecewise and then letting the CAS evaluate things from there. So firstly, let me just clear A to Z actually, just rip all of this stuff out of the CAS. Make up the piecewise function is equal to piecewise k times 3 take x, k times bracket 3 take x. That one is for 0 to 3. Less than equal to x less than equal to 3. And then very similar, x time k times x take 3. That one is from 3 to 6. 3 less than equal to x less than equal to 6. Piecewise sorted. Sketch the graph is now quite easy. In fact, I think we've sketched this exact graph before. You would have k as your... Oh no, it is offset, isn't it? This one you kind of got to do by hand, unless you want to use the slider and, you know, have a particular value of k. It is just linear, ultimately, at the end of the day. So if we sort that out, so the first function, y-intercept and x-intercept. X-intercept let y equals 0. You're now doing x equals 3. So x equals 3 is cut. And it's a negative gradient, so it's going downwards. Y-intercept let x equals 0. That's going to be 3k. Cool. And then the other way around, again, it's going to have the same x-intercept, but this time going up, and because the horizontal distance is effectively the same, it's going to again cap out at 3k. So your area under curve is effectively two triangles here. That should add up to 1. Hence or otherwise find the value of k. Well, yeah, this should now all add up to 1. If I integrate from 0 to 6, h of x dx, do I get 1? Oh, sorry, we're finding the value of k. Yeah, my bad. So it's a matter of solving that to equal 1 and then solving for k. Which, well, you probably could have seen from there. K should be 1 over 9. We've hit time, but I might as well just finish them off. So verify the mean of x is 3. This is the whole x times f of x thing. I wonder if this will break. So 0 to 6, x times function. Yeah, okay, that's not great. So, what do you do when stuff like the mean and variance breaks for piecewise functions? You do it separately for each individual little bit, and then you add across the two results. So what you would be doing instead would be 0 to 3 x times the function. I wonder, did it break because I just had no k in there? Let me just quickly define k. Maybe it was my fault for not putting k as an actual thing. It was my fault. Okay, so Control Enter on that, making sure you've got as much defined as possible. Verifying the mean of x is 3. Well, there we go. We just got our 3. Find variance. So now that we have our mean, we can now do x minus the mean, all squared, times the function. X minus the mean of 3, all squared, times the function, 4.5. If you needed a standard deviation, you would just square root that value. Alright, that's about it. So we looked at the mean, standard deviation, interquartile range, and we did a little bit on... actually no, interquartile range is part of doing the percentiles, so yeah. Was there anything we didn't do? Technically we didn't do exactly the median, but that would just be doing the 50th percentile. Yeah, happy to stick around for a little bit longer if need be. Are there any clarifications necessary? If not, thanks for coming.
Thank you.
Thank you.
I've got a question. So
Yeah.
I forgot, but did you say you post the class recordings at the end of the week or the start of the next week?
Yeah, so it's supposed to be end of the week. I've been more or less dealing with sickness, so I think it's been a little bit lax. But yes, end of week is what it's supposed to be.
Okay. All right. Thanks. Have
Yeah,
a
no
good
worries.
weekend.
You too. Take care.